aneurysm, but making that most of the flow goes through and only a small part of it enters the aneurysm. This is going to make that the flow pattern inside the aneurysm is more simple. This will hopefully lead to thrombosis inside and occlusion. Okay, the thing is, we have the doctors that decide that the patient needs a stent. Now, the next question is, which stent are we going to use? And the answer is unclear, because it's not easy to guess, and mainly the effect is going to depend on the specific geometry of the aneurysm. The whole geometry of the system can change completely the flow pattern inside. So it's not easy to guess. And in fact, that's what doctors have to do most of the time, guessing or trial and error. Sometimes it's the case that they introduce one stent and then they see that they need to introduce a second one and they expand it inside the first one. So here, CFD to the rescue. CFD simulations in this patient-specific geometry can help. It gives the possibility to study what is the effect before doing the procedure. The idea is that we will be able in the future to help doctors decide which treatment is the best and what are the best geometry of the stent for a specific patient. Of course, doing this requires a lot of work, and a typical pipeline is also how I'm showing here. The first step is the obtention of the image, or we start at least with the image. This is a 3D image of the patient acquired with angiography or CT. From the image, we need to segmentate the image and we create a model. This model is the one that we are going to use to generate the mesh. From there, we can, at this point, with a lot of work in between, do the simulations. These steps are probably the most difficult at the beginning because there is like a lot of graph work to do there. In case we want to also simulate the influence of the stent, here we need to add a couple of more steps. First, we need to deploy one cylinder, and then we map the geometry of the stent in this cylinder, and then we run a simulation considering the influence of the wires on the flow pattern. Of course, this is something that has several challenges at different levels. One of the first challenges is to determine what are the uncertainties of the simulations. It's super difficult. It's very difficult to know what is really going on inside the aneurysm of the patient. So, in order to bound the errors or to know what's going on or how close are we of the simulation, we were working with models and we were trying to make a comparison between the simulations and the experiments to have a guess or a feeling or where were we standing. So this is a more large study, but basically we follow an aneurysm in longitudinal study over a couple of years, and then we created all the models in plastic, and then we did the experiment and measure all the velocities inside the area of the aneurysm. This is the aneurysm, this is the parallel arteries, we try to reproduce the same flow pattern in our simulations, and from there we could estimate some approaches to the errors that we have inside the algorithm between our simulations and the experiments. This is only one approach of the possible uncertainties that we have there. We don't know how the boundary conditions are. We don't know how the profile of the fluid is entering. We don't know what's going on there. How close are we from our assumptions of rigidness of the wall? So it's a difficult issue. We have to think of the possibilities that we have here, where we can divert from the reality. But in the end, the conclusions were that we were not that far from at least reproducing the experimental results. The following challenge is being able to reproduce the wires that we want to model. This is, by the way, this is not exactly what we are trying to reproduce. This is only a photo that I put here, so you know more or less what the real thing and what we need to reproduce. This is the actual simulation with the immerse method, and this is a deploy extent. This requires a lot of work, but at this point in the group, when we were working on it, we have this part of the methodology mostly figured out. The other challenge is, how do we take these simulations to the clinic? The problem that we are approaching here is that we cannot afford the 2 weeks, let's say, that it takes this simulation. We need something that we mostly accurate in hours, at least. We are aiming of having a study that takes like an X-ray study. The other problem here in the clinic is that we need to make the creation of the models it has to be a process that will be more easy to do or more simple. Still, it's very, it requires a lot of experience. But well, at this week we were in this issue, we were concentrating on first trying to reduce the time. For this, we propose to replace the wires with one solid porous material. So we are trying to avoid to refine too much the meshes around, not around, but in the area of the wires here. We tried this approach, which I'm going to show in the following slides, and we obtained very good results. This is actually some results to compare. We found a good reduction in time and hardware requirements. So, entering this first, to mention how do we add this porous material to the solver. We do it by adding a source term, basically to the right-hand side of the momentum equation. This source term is representing the pressure drop or the pressure gradient inside the material, and we are modeling this with the Darcy-Forchheimer's law. So we are assuming a linear and a quadratic dependency on the velocity. This is the easy part. The second challenge here is to find what are actually these two coefficients, D and F. For this, we try two approaches, and both are working. One is obtaining those coefficients from empirical curves. We have our analytical formula based on experiments, and the other approach is by doing the simulations of the mesh that we want to model with these coefficients. I'm going to briefly show one example of how would it be to model or to obtain these coefficients. Here we have one of the correlation for one specific geometry of one stent. This is a correlation that it takes, it's not that easy to find in literature. In fact, I spent like 6 months probably for my PhD tracking the paper where we can find the different correlations for different types of possible meshes. But once we have this, we only need to introduce the geometric parameters here. Characteristic longitude, the porosity parameters. From there, we relate this to expression for the pressure drop. And from there, we can easily find an analytic expression for the coefficients T and F that we are working. So we don't need to do anything too complicated here, only plug numbers and we found our coefficients. The second way, this is probably it requires more work, but it's more general in case we don't have the analytic expression or our mesh is too complicated. We can find these coefficients by doing a simulation. In this case, we have the mesh, we have a flow that's going through it, and we just need to measure the pressure drop before and after the mesh. We construct this curve, and based on this curve, we can obtain our D and F parameters. So we have both ways, both work pretty well. I'm going to show just a brief example of which are the parameters. This is our geometry. This is, by the way, this is a super simple case that I'm showing here, but we can extrapolate this to more complicated cases. In fact, real stents are much more complicated than this. It have different wires, diameters, different range of the wires. It's not that regular, but basically the idea would be the same. We will have our geometric parameters here, the parameters of the fluid, and from there we obtain the parameters that our model is using. Basically, we're obtaining the beta and the hydraulic diameter. With this, in the case that we are using the analytic expression, there is nothing to do. We just plug it and we obtain our two coefficients. In the case of the simulation, we have to do something like what is shown there to the left. We obtain our curve and we obtain our parameters. These are different, but they are close enough. This is just the validation of our results. We are comparing here the porous method. I'm probably going ahead here and showing results before showing how we obtained it, but I wanted to finish with the questions fast. So the red dots here are the results obtained with the porous method. The blue dots are the results obtained with the traditional immersed method that we were using at the lab. In green, we have other results from the literature, and the analytic expressions are the lines. We found that all the results were the correlation was very good for our uses. So we have more confidence in our model. So we have, at this point, the solver that resolves the porous material. We have a way to find our coefficients of the stent. The third step that is missing here is define the areas in the geometry where we are going to apply this porous material. Basically, we need to find a way to, based on the geometry, to find where are the patches that requires this extra material. Basically, what we are going to do is to expand a cylinder inside the artery. We are going to create some patches, and these patches are going to be our source for the densification of the mesh. In detail, this is done by deploying the cylinder. We need to expand this until just it crosses the artery wall. The artery wall is going to cut this cylinder, and we are going to remove the exterior part. This leaves us with these patches. Here we contracted only small displacement, only one element, and we need to close the gaps, close the sections, so there is no fluid that can go through this way. So with this patch are going to have two uses. The first use is a source for the densification of our mesh. Our mesh, this requires some parameters that we need to define for our simulation, but basically we have to decide on the factor that we are going to reduce. It's not that much, only one splitting in half, or probably two splits is enough, and then decide on the thickness of the area that we want to densify. Then we are going to use this patch here too as sources for our solver. Our solver is going to compute the regions for the porous material based on the distance to this patch. Once that we combine all this, we start to getting results. This is a comparison for one of the algorithms. In the top row, we have the traditional simulation using all the wires. We are looking at the streamlines, velocity isosurfaces, and wall shear stress. We are typical parameters that we watch in this type of studies. Below, we can see the results using the porous material. We can see that qualitatively, at least, the results are pretty similar. The same for other combinations of aneurysms with stents, give us again pretty close results. Here the results are the matters are in the area of the aneurysms. These are results that come from the stents against the wall, but it doesn't matter. Finally, this is a super difficult case to model. This is very huge aneurysms without a clear definition of the artery in the inside. So basically, it's a big ball, one artery that enters and another that leaves. So we have to guess where will be this imaginary stent crossing it. In this case, the results are not that similar. For example, there is this jet that is missing here. If you ask me what's the real solution, I don't know. This might be produced only because of the effect of the wire. So it's difficult to tell which solution here is the most the realistic. But qualitatively, at least, the comparison between the two methods is close. Some quantitative comparison of some of the typical parameters that we observe or try to use to measure our solutions. We see the three different stents using three different aneurysms. The difference depends on the geometry, for sure. It's not that bad. It's probably the worst case. This is the aneurysm number 3. It's the big ball there. But this probably is an extreme case. For the other cases, we are pretty close. We are ballpark. Regarding the reductions that we are obtaining, if we compare the size of the meshes with the original method that we were getting, using the immersed method, that it will be this one. We compare with the meshes that we are constructing for the porous method, we see a very big reduction. We are going from almost 70 millions of elements to between 10 and 5, depending on the case. These numbers, the blue is the immersed case. So the reductions are important in the number of elements and the subsequent reduction in memory. Regarding times, we also see that the reduction is also important. We are going from, for example, 8 hours here to 5 minutes in the simulation. These are times for the first step of the study. Okay, and until this point, this is a comparison between in our internal simulations in our group, because we are comparing the way that we were doing it before and the way that we were doing with this method. But to be fair, we need to compare. This is not totally fair because we are assuming in the porous method that we are applying the porous material only in patches. But the other way of doing the simulation implies that we are modifying or refining the whole artery, parent artery. So if we really want to see what the improvement of this technique, we need to adjust the areas to the same area in both cases. When we do this correction, we find that still we have huge savings in elements. We are, for example, in this case, going from 16 million of elements to 5 million of elements. So we are still getting huge reductions in time and in memory. Well, so the conclusions of this is that we are getting a methodology that is fast, general. We can simulate any stent that we can normally have, and it's relatively simple to simulate these stents in patient-specific geometry. The precision of our method depends on the geometry. There are cases that are more accurate to model than others. But again, the results are bounded by the uncertainties of this type of simulation. We are not sure what the real results are here, so it's difficult to guess what's the real solution. Well, we are a step close to the requirements for the use of this technique in the clinic, which is low simulation times and low hardware requirements. And well, that's all. Thank you very much. Have any questions? Please shoot.
I have just 2 questions. Okay? Well, the first question is related with the AD or DF parameters.
Yes.
Have you studied from different types of cell, different types of stems? Because the geometry of the stems are different. So
Yes, yes.
But how do you study? How do you validate these parameters?
Well, this is
numerically or just experimentally? Or?
well both. These parameters are basically so. This is one of the basic models for porous material. So we have this correlation. So besides the stance, we have analytic expressions, which are this kind of expression for different type of meshes. These correlations are very good, and we try all the experiments or the computations that we did give us that they were pretty good assumptions. As I said, in the case that we don't have these expressions, there is another way of doing it, which is by, let's say, brute force, which is simulating these parameters. And this is the way that one will obtain it. Like computing this curve, from this curve we can get two parameters, the linear and the quadratic, and we can easily associate these parameters to D and F.
Okay, but you studied this curve for different types of stems.
Yes, yes, yes. You can simulate any stent that you have, because you are doing the experiment and you are obtaining this curve for any geometry that you want to put there on the tube.
And the other question is, you work with when you do your simulation, is it steady state or is just type of solvent that you use?
It's pulsated with a couple of cycles.
But you get a steady state or you get just a dynamic solution? Or?
Well, no, it's standard in all the studies that we were doing, but we try to find. We give it a couple of cycles to adjust, and then we take the last 2 cycles, but we simulate like 10 cycles. So I don't remember the number exactly, but it's something around that.
How long take the simulation, the full simulation, just with the 10 cycles?
Well, it's in the order of 2 weeks.
2 weeks.
Yeah. It can be more or less depending on the geometry and the size. But
okay, but in conclusion, they put just time and power requirement and goes to the clinic. So this was my question.
Well, for the other, you mean sorry, you mean with the porous?
Yeah, we have one case, for example, just take the memory, just make the segmentation with the model, just porous material, everything. How long it takes?
The whole process of constructing this?
Whole process. It's thinking that I go to the clinic, to the hospital, have an error, I take it.
Probably, if you have experience, what it takes the most time here is constructing the model. This is by far this is the most complicated case.
Okay.
It can take a day for a difficult case, being optimistic. In fact, this case, I did it myself, this case, you can see here that the image is solid, it's not separated here. So from the image, if you segmentate this, you are going to have one solid surface. So I had to cut it by hand, turning off voxels here, and then make something that is realistic, that is not too artificial. This process is the most complicated. It took me probably 3 days, in this case, working only on this. But yes, I probably segmented more than 100 cases. So I could say that in the end, over the 2 years. So I could say I was an expert at the time working on that.
You use the RAL.
Yes, exactly. So it takes a person to some experience to being able to create these models. Meshing this takes time, and this is the most complicated case for the, not complicated, but the memory consumption for creating the mesh is 10 times worse than for running the simulation. Probably, yes, we are on the order of hundreds of gigs of RAM for meshing this model. And then the simulation is not that heavy on the memory.
How fast is simulation? Computational environment. Only the simulation, the TFT.
Well, it was in the order of 12 hours. Yes, from the 2 weeks with the immerse method, we passed to 12 hours with the porous method. Yes, and for what I show there is the result is that for the first term, we went from 8 hours to 5 minutes. The first iteration only from the 2 weeks. I take only the first step, which is the most complicated, right? Because it's the most. But well, we can say that we are in the order of a day for obtaining one study, which is similar to what other type of studies takes. Like if you are in a magnetic resonance, is going to, until you get the results, is going to do this. But this was actually developed for being implemented in devices. This was in part funded by Philip. They have the devices for angiography or CT, and they wanted to make the acquisition of the image and automatically detect and making the simulation of the aneurysms. So we were very focused on those times. Your question? Okay, well, thank you very much.